My first job as an engineer was at Disney. I was at Disney Animation in 2014-ish. This is the first time that I worked at a place where I wasn't just a consumer of technology. Right? I'd been a sysadmin for a while. I was running stuff. I was plugging it together. I was reading the docs and saying like, oh, this is how this thing's supposed to run. We'll run that thing over here. We'll write a couple bash scripts and use it. And now I'm at this place where I come in and they're like, oh yeah, we wrote our own orchestrator for our jobs. And that's like, we have rendering jobs, we have all this scheduling we have to do. They wrote their own renderer. I'm like, wait, you're creating technology here? Like, how does that work? Like, I don't understand the economics of not invented here, which is what is common at a lot of places. Like, no, we have to build it ourselves. I'm like, no. I've been a consumer of technology my entire career before this. And so this is the first time that I'm like, okay, what does this look like to build something yourself, and why would you build it yourself? And then I went down this rabbit hole of like how our orchestrator worked for our jobs. And I was like, if only I could learn from other orchestrators. If only I can see what other people were doing and see how it compares and see what is different. And so I went down this rabbit hole of realizing that people publish what they do. And it's free out there online in a lot of cases. And you can go read a white paper. And I got addicted to reading white papers. I'm like, this is where the source of truth is on maybe what the intention of this system is, but not necessarily the implementation always. So some of these orchestrators are things that I have used. Most of them I have not, because I've read white papers about them, I've talked to people, I've watched a lot of conference talks, but it was not a case where I was like, oh, I'm going to run all these things. I'm like, no, I want to see why they were built, who was building them, and what their intentions were. And thankfully, this talk is right before lunch, and so I don't have to stay to 30 minutes, right? We can all stick around. The first one that I found was Mesos. And Mesos was very, very popular at the time. If you were in container space early on, you knew Mesos. Like, it was a thing that existed. By the way, all the QR codes should go to the white paper that I screenshot, or a home page if there's not a white paper. But one of the cool things about white papers is like they link to all their other sources. And so you can spend literally all your time just linking out to, it's like Wikipedia for academics, right? Like deeply reviewed content. And so when I was reading the Mesos white paper, I'm like, what did they do? Why did they build this thing? What was this for? And the primary reason it was built was for HPC workloads in a non-HPC environment. And so high performance computing, if you're not familiar, is usually a bunch of servers that are interconnected really, really fast. Like the network side of HPC is what usually makes HPC HPC. If you just take a bunch of servers and put them in a room, it's not HPC, that's just a bunch of servers in a room, and usually your data's slow, all this stuff becomes a problem. So Mesos was built so that they could have HPC-like workloads in non-HPC environments. And I'm like, that's really cool. Why? Again, what are you doing here? And how are you architecting this thing? The main things with Mesos that I really wish Kubernetes would do is Mesos itself is almost nothing. Mesos is the piece that gathers all the information from all the nodes. How do I do that? It connects all the things from all the nodes in a very thin layer, and then it has what's called a framework on top of it. I don't know if that's me. Anyway, it's the same picture. You all see it. Everything on top of it is a framework. And a framework is basically platform engineering, right? The Mesos failed because they had bad branding. No one wants a framework, they want a platform. And this was a problem at the time. But the Mesos layer was like this super stable, small layer of just like, hey, let me gather all the resources. And when you want to run something, you talk to the framework. You don't talk to me. The framework talks to me. So they have this two-level scheduler that's like, you talk to the framework talks to Mesos. Mesos then sends an offer back and says, hey, here you go, this is what I know about. Take it or leave it. And a lot of times the frameworks say, no, thank you. They can do that. But that was the really cool thing about Mesos was this minimal layer, which then allowed it to scale really big. Because your frameworks don't have to be as big as your Mesos cluster. It takes all of these nodes. The white paper points out that they did a node test in a cluster. And again, this is more than 10 years old now, 50,000 nodes in a single cluster. 50,000 nodes in a single cluster. The limitation they ran into was EC2 at the time. The throughput of a NIC on EC2 couldn't handle more than 50,000 nodes. And like, we think this will scale easily up to 100,000 nodes. Like, no problem, we could do it. We don't have the compute capacity somewhere to run this. That gives us that much throughput, because it was 1 gig NICs on EC2 at the time. And because they kept those layerings of frameworks, platforms as we would call them today, and a minimal, this is where the resource live, you could do that. The other cool thing was these frameworks could be super duper opinionated. And so a lot of the HPC frameworks were, we want to scale this workload. There's a couple seats here if you want. You're right up front. It's okay. I don't think I smell too bad. But you could literally, frameworks would consolidate like some grouping of the rest of the machines. So you could have 50,000 machines and the framework's like, actually, I just want 5,000 over here and I'm fine. And you could do that by divvying that up, and then the framework could be opinionated about like where the job's gonna run. Again, HPC workloads, data is really important, and if you're doing it in a place that doesn't have a lot of network throughput, like actually I wanna move the job where the data is. I don't wanna move the data to the job. And it could do that in the framework. Really cool, really important. The biggest downside here is this little zookeeper quorum. If you ever run zookeeper, that was another bad thing about Mesos. And so it had to do this for the Mesos side. Frameworks can keep their data somewhere else. So again, frameworks could scale different. They didn't all rely on etcd as the CRD backend. A framework is completely separate. The next thing I found after Mesos was Borg. And everyone knows Borg, right? No one's ever used Borg. Everyone knows about Borg. It's the most successful platform in the world, right? If you're looking at platform engineering, this is the thing everyone says you should use. And the reason this exists is because the actual org chart at a company. Like, you can't build Borg at AWS. Not gonna happen. AWS is the pizza teams. It's all independent. It's all this stuff. Google is very centralized. They have a monorepo. They have centralized teams that do all this stuff to consolidate the expertise into a single place, and that's why Borg works. It's not because it's a better technology or something, it's an org chart reaction, okay? Like just straight up. And Kubernetes does this because a lot of enterprises do centralized teams. They're not the AWS pizza team model. They are org chart style, all the DBAs go over here, because they're expensive and we just share them out to all the other places. And that's what Borg, SRE does the same thing, right? Like SRE is a centralized IT team that does that. Go look on Amazon's website, there's no SRE job title. Like it just doesn't exist because they don't centralize that stuff. Borg breaks up their clusters into cells. And that is the coolest name for any sort of cluster you can have. And everyone's like, I want cell-based architecture because cells are cool. Because Google does them, right? And it's like, actually, it's a cluster, it's okay. We can call these things different, and maybe Kubernetes should have called them cells. I don't know. But the surprising things about the Borg paper is, which maybe Kubernetes should do better, is they mix their workloads, HPC and long running. Mesos could do some of that, but it's separated by frameworks again. Borg is, no, we can do jobs, we can do long running, and we do prod and non-prod in the same cluster. You talk to anyone starting out in Kubernetes, that is an anti-pattern. Like, don't do that. You have a non-production Kubernetes, you have a production Kubernetes. Those things should never mix, right? Borg's like, nah, we got this. If you, and again, I never used it, white paper reading. If you are a consumer of Borg, you have infinite capacity at the lowest tier of priority. Everyone that uses Borg could just say, run 1 billion jobs, and Borg's like, sure, I don't care. You're gonna get preemptive. I don't know if I can. And it doesn't matter because they have this really good, Kubernetes has tiering of workloads too, but there's no concept of like, how do you overprescribe on job priority? And the first time I saw someone actually run a live demo against a Borg cluster, they ran 1,000 jobs or tasks, replicas, and the last like 10 never scheduled. They're like, oh, doesn't matter. It just doesn't matter. It's fine. Like we never will get there, and it doesn't matter that we never will get there because we didn't ever expect to. The expectations of using the system in a prod and non-prod way is completely different than how you expect. I got to go to the dev Kubernetes cluster. I got to go to staging. I got to go over here. Like now, you mix it all together. The reason Borg, and Borg was scaling up to 10,000 nodes in a cell. The reason that works is the Borg master here runs an in-memory database. Like it turns out, like if you just make your database really, really fast, like you could scale higher. Like that works, right? You can throw money at the problem and just like, oh, you know what? Let's put this in memory. And then when a Borg master would fail, it would snapshot to disk, and in order to like replicate over somewhere else, it would have to like go read from the disk. It's like, oh, like hold on, we're gonna be down for a little bit. We're gonna just replicate. And it's just like, no, downtime's okay. We're not looking at total HA, high high availability side of things. It's like, no, if it goes down, and in the Borg paper, they even call it has 4 nines of availability. I'm like, that's actually some downtime, right? If you calculate that out, like this is gonna take some time to replicate between these things, and people are just okay with that because eventually it's gonna get there. The things that I think Borg did wrong, and they call it out in this paper and other papers, every job used the node's IP address. Every container on the system used the node's IP address and then mapped ports. And it's just like, oh, everyone gets the same IP because it's a node. So if the workload goes away, the port would also change. And so you had all this complexity on where's the workload exist. The IPs address have changed, the ports have changed. That side of it became really difficult. And that's why like networking works the way it does in Kubernetes. Like we just want flat networking, you get the same IP address, doesn't matter. That's literally a lesson that they learned here. The other thing I found super fascinating is like in this paper they had a command line called Borg SSH. Like literally you would SSH into your pod that ran an SSH daemon to connect to it. And they're like, this was so much better because everyone used to SSH into hosts. And then they'd find their workload on the host and they had access to the whole thing. Like every SRE and person that says like, don't SSH into prod, Google does it or did it and calls it out. It's okay, it's a thing. You have to debug things sometimes. And you know, lots of things have changed. I think now the database is separate. Again, these papers are a little bit old, but they're fascinating. My favorite orchestrator is Twine. This comes out of, it was called Tupperware when it was Facebook, and it's now called Twine. So you can find an old Tupperware paper. The Tupperware paper is a lot of the similar stuff, but Twine, I think they got brands, you know, sometimes complain about things when you call it something your brand. The thing that Twine is amazing about is they're like, we run one Twine cluster in a region. And if you know Meta's scale, that's about 1 million machines. And they call it, like one cluster is 1 million machines. In this paper they say we're not quite there yet, but they're getting there. And like we know this will scale. And the reason that scales is because they shard the API server. They're like, guess what? Instead of making it all HA, we just take, here's a load balancer, and here's a shard for this amount of the cluster, and here's a shard for this amount of cluster, and that's not only the API server portion of it, that's also the database portion. Like, no, we just have duplicated data across different things, and we can have HA shards. Like, you can scale things different. Kubernetes load balancer in front of a couple API servers. Ooh, that's fun. And as soon as you put like 2 HA API servers, one of them is the primary one. All the writes have to go through the one, right? There's no sharding. And then once you go to the database, etcd, one of them is the primary, and you can't go to the other ones. And you're just like slowing down all this stuff, and you're making it less scalable. You're never gonna get large-scale systems like 1 million nodes in a cluster by doing these single points of failure with HA. That's not how it works. So super fascinating. In this paper, they call out multiple times. They're like, we are not Kubernetes Federation. We do sharding because sharding works. And if you go read other papers like Route 53, Amazon has a great Route 53 paper that calls shuffle sharding. They have a blog post about it too. It's like, here's how we break up customers in Route 53. And we shard the data. And we just have a bunch of them out there, and they're all behind load balancers, and we route to the people. The other cool thing about Twine, which is still the same picture, I haven't changed slides, is they have what's called host profiles. Host profiles will change the actual node to be optimized for the workloads that are going to land on it. They actually go through and they say, actually, we can, instead of changing hardware, because in a Twine cluster, almost all of the machines are the same. Almost all of them are a single socket, single sled. Mesos and Borg, not the same. They're like, we're gonna take a bunch of different stuff and put it together. Twine's like, actually, we're just gonna buy a bunch of the same stuff. We build it ourselves, go to Open Compute, you can see what they're building, and it's all single socket stuff. And they're like, actually, by doing single machine hardware everywhere, we're saving 17% total cost of ownership. Just what if you just reduced all of your cloud bill by 17%? That'd be really cool, right? But also, they can do these things called host profiles, which optimize the node OS for your workload. So if you're running HPC or web services or ML jobs, it's going to say, actually, I'm going to tune this node to be good for your workload before I put the workload on it. And then some kernel tuning. Like right now, we're all like lowest common denominator, right? We're like, we're going to keep the defaults, and this is probably okay. And also tuning's hard, right? Like I don't want to go in there and like mess with the kernel stuff because who knows if I'm going to break it, and all those things are a problem. But they optimize. They have 17 different host profiles, and a node on average switches every 2 days. And so it'll run some workloads for a little while, and it'll optimize for that. And by doing that, they increase their throughput of their web service, the main thing that Meta does, throughput increased by 11%. It was like, actually, what if we just make things 11% faster and better and cheaper? Like we just spend less on that. I'm like, that sounds amazing, right? Like I would love that. I wish Kubernetes had that concept of being able to tune the machine instead of just saying everything's the same. Here we go, you get the Linux kernel, maybe you get this driver or that one, right? Like you can do some labels and like try to isolate things manually, but we're just going back to like that's your server, this is my server, right? Being able to do that dynamically and being able to have the workload say, I need something like this, or I am this type of workload, please give me more I/O throughputs. Please give me something along these lines would be fantastic, and I wish Kubernetes would do that. The other thing Twine does, it has 2 types of schedulers. It points out here in the picture. They have an allocator, which is like the fast, I'm just going to get this job running. It came in, here you go, and then they have a rescheduler that goes in and like optimizes the long, like, hey, I see what's been running over time. I can actually like, oh, this host profile is available over here. Now I'm going to move you where you should be, and you're going to be faster. And I'm going to do these optimizations long term. And Kubernetes has like the descheduler and stuff, but almost all of those are just like, throw it back to the scheduler, right? Like, oh, it's just like, mix it all up, we're going to auto-scale some stuff, and then we're going to throw it back to the scheduler, and hopefully it does good, right? But the scheduler has to be fast. The scheduler wants to do things quickly. And in this case, we're like, actually, we can override the scheduler with our long-term rescheduler that's going to do these harder math problems and say, I could reduce the usage of the cluster by 10 or 20% by like reshuffling all this stuff and knowing where it's supposed to go. And this is one of those things that Carpenter does. In AWS, Carpenter does it fairly well where it actually does this like reshuffling just based on changing the machine types, not on host profiles or things in the kernel. It's just saying, hey, I know a different machine type is going to fit your job better, so we're going to move there. The last thing that I think is amazing from Twine is if you have a big batch job, you're going to schedule 1,000 jobs in this batch job, and they're all going to schedule, and then you don't need them to run right away, right? Like, they're just like, oh, just have a long queue. It's fine. They'll come in. We'll do some stuff. It'll get there eventually. The batch jobs will all finish. What Twine does is it allocates a handful of those batch jobs and says, hey, I know all the other jobs look exactly the same. So instead of going back through the scheduler every time I need a new one, I'm actually just going to keep this job section open, and I literally can just pull in your job underneath, and it literally will replace the containers that's there with a new job. And it's like, actually, we didn't have to do any rescheduling. We didn't have to reallocate anything. We can just take the new data, take the new runtime thing, just plug it in there, and they get more throughput for their jobs to not have to go through the full cycle of, let me auto-scale this, let me find a host profile, let me do all these things in a way that is super inefficient if you're going to run the same thing 1,000 times. And you can just reuse it. And that's what we used to do on servers, and we kind of lost that. But now they have that built into Twine, where your job, if you're running batch, can just say, like, actually, I don't need to allocate all 1,000. I'm not going to put them all in a queue. I'm going to let the job itself have its own queue and just reuse the same thing I allocated. It's just going to run longer. Super fascinating. As much as Twine says they are not Kubernetes, they do not do federation, at the very end of this white paper, they call out, actually, federation is good for some things. Federation is good for global services. They have this notion of you can run a service and it's globally available, and that's really bad when we try to hide all the magic from you. When we say, like, actually, we'll take care of it. Because sometimes people have opinions about where their jobs should run. They know better than the scheduler what's going on. And so they are moving to a sharded in-region, federated cross-region notion. So they're able to do some of those things. 5 minutes? No, it's lunchtime after. We're not doing 5 minutes. I'm kidding. And that's really cool. I don't think they got everything right with Twine, but I think that some of those things, the host profiles, the batch jobs, and the sharding for the scalability are key things that like Kubernetes does none of, and I think it'd be amazing if it did. By the way, I work at Sidera, and we have like an API for tuning jobs, and it's like one of those things that I want to do, host profiles for Kubernetes. If you're interested in something like that, let me know. Docker Swarm. I remember when I was at DockerCon when it was announced. And I'm like, oh man, that init command was amazing. I'm like, Lucas here is like, yeah, like it was like you had a cluster. Like that was so cool. Like how would you, and the fact that it was built into Docker Engine, like everyone was running Docker Engine at that time. We didn't have other runtimes that were popular. Like everyone just had Docker everywhere, right? And the thing that was so cool about was like, if you ever exported Docker host, has anyone ever done that? Like there's an API on another box, you like export Docker host, I can run Docker commands against that thing. And like that's how Swarm felt. It was just like a really big Docker host. And people did that for years and years, where it's like, I can just call the Docker API from somewhere else. And the coolest thing about Swarm was that init command, which now we kind of have with kubeadm, and people are doing that, and we have all the stages. kubeadm is much more complex than Docker Swarm was because it has a lot more flexibility in how things are supposed to work. But the fact that it was just like, you're going to have a container runtime, you're going to get this thing built in, and we're going to do that flow of like joining machines, all that sort of stuff, is great. The downsides of Docker Swarm was there was no hard way. There was no, like Kubernetes the hard way. How many people learn Kubernetes from Kubernetes the hard way, right? Like there was no magic anymore because you could see, oh, this is how this thing works. I don't ship magic to production. It's just not, it's against my policy. Like if something is magic, I'm not going to be on call for it. Okay, like that's just a low bar, okay? And Docker Swarm always felt like magic because there was no hard way to get it running. Everything was too easy and too taken care of. It was really cool though when I don't actually want Kubernetes. I just want a Docker host somewhere, right? Like just take care of some of that stuff for me and maybe occasionally I'll fail over, right? That stuff was really cool. Anyone use Nomad? Yeah, there you go, Joe. Fantastic. It's the only one that stayed with this single binary approach. Like my first Kubernetes cluster was the Hypercube, which was like a kind of single binary, but it was like a gig. It was ridiculous, but Nomad was always just like, no, we are for real, like a single binary. We build the networking in, we're gonna build the key value store in, we're gonna do all that stuff out of the box. You don't have to do it. It's kind of like the Docker Swarm Kubernetes had a baby, which is really cool. The things that I love about Nomad and Kubernetes does not do, and again, it's something that I wish they would learn, is they have this notion of multi-region clusters. Like, who'd have thought? Like, you could span a region with a cluster. It's like, actually, we don't care because we have console, and also the guarantees around it are, this can be slow. Console uses gossip. We doesn't have to be fast. Kubernetes optimized for, we have fast return trends from the API. Nomad's like, yeah, we'll get there. It's okay. Like, you're going to get your job. Don't worry about it. We're going to gossip our way to the point of this thing's going to work. And you can do that across regions, which is really cool. And if you have multiple clusters in multiple regions, you can also gossip the clusters together. So you could discover, where the hell is my workload running? Right? And you can query one cluster, and it'll go find it in another cluster. It's not replicating data. It's not doing any of this like, oh, we have to make this all federated. It's like, no. It's like a transparent discovery of like, I know it exists. Please tell me where it is. Really cool things. Again, I think Kubernetes could do really well by at least copying some of these things. The multi-region clusters would be awesome. At Sidera, we have a similar thing with Talos. Again, where we get a free hat. We have a WireGuard link that goes between them, and you can run them across regions, and it's fine. Like, that stuff actually just works. You don't have to stick to this like fast sort of like, we always have to reply really quickly. This thing's going to be okay. ECS, last one on the list. ECS, I use this to build Disney+. I was in charge of the infrastructure at Disney+ when it launched. I think that Disney+ would have completely failed if we did not have ECS. ECS was fantastic for us as a 4-person team, running all of it in a containerized orchestrator. When we were deciding on it, the thing that I love best about ECS is the API has no versions. 0 versions. You never have to upgrade an ECS cluster. And I'm never forced to upgrade an ECS cluster, and I get to choose when I upgrade, and when I change my nodes, when I change the daemon on the node, the API changes. And that's the only time. You can't go backwards, but I could change that on the node. I can say, actually, I'm ready to update, and now I'm going to redeploy all my nodes, and here you go, ECS, please change the API for me. I get the new features when I'm ready, which I think is something that is really, really difficult on the ECS side, and it makes it hard to change some things. So you got backwards compatibility for infinity, but I wish that Kubernetes had a versionless API that was stable, and you only upgrade it when you needed to. One more thing, Nomad. It scales really well. Everything's in memory. It's fascinating. Again, just like Borg, if you want to scale something, throw money at it. They have this challenge. You can go read it, and it scales up to like 7,000, 10,000 nodes or something like that. And the scheduler is like using 100 gigs of RAM. And it's like, yep, that'll work. Fast disk, you're good. So that's it. We actually, Sidera, we're doing a workshop here. Most of these schedulers were designed for on-prem. Most of them were designed to run in metal environments, and that's what we do focus on. We're literally here, not in this room, but at this co-working space on Tuesday. So if you want to come back on Tuesday afternoon, we're doing a workshop. We have free drinks and dinner afterwards. Come find me or sign up there. We still have some slots available. So thank you very much.
All right, we have a few minutes for questions. Anyone?
It is lunchtime. You can free to go, but
no, we have time for questions.
Really nice talk, thank you. I feel like a lot of the orchestrators that you've talked about are finding different points on the, like, how much is centralized in the controller or like the orchestrator's scheduler and all of that versus how much is kind of like spread out into different control loops or even like into the application itself. So I'm kind of curious, like, if you were to build your ideal orchestrator, like, would you have everything kind of split apart into these little individual control loops, kind of like Kubernetes does, or do you want things more centralized?
No ideal orchestrator exists. That's a problem, right? Everything's trade-offs. All of these things, they all had design decisions and trade-offs. When I look at what Facebook was doing with Twine, they are primarily on-prem. They're not auto-scaling, right? Like, no, we have to use the resources. We have to fit within the budget of the machines that we bought. And we can do that different ways. We can optimize the hardware, we can do different stuff. And so all of its trade-offs, I do think that Kubernetes has overemphasized on making it easy to extend things, and all of the reliance on CRDs and then throwing everything at the API server with no sharding ability, no way to like remove some of that is like, actually, I just need a new etcd cluster. That's a high bar to get over. To say like, actually the beginning point of Kubernetes has always been hard, because we make it so flexible to do everything that we think you might want and not have some more opinions about, no, don't do that. Like, it's okay, like in Nomad and Docker Swarm are good examples of that. Like, actually, they're just gonna restrict some things you can do and make it easier for you to kind of run it over time. If you wanna ask a question, come in.
One of the things about Nomad, and Hashicorp uses this as a differentiator with Kubernetes, is it is agnostic as to the workload. It might be a container workload, it might not. And CoreOS Fleet, which preceded Kubernetes, was the same way. It was like, hey, you're going to run a systemd unit, and if that systemd unit happens to run a container, great. If not, also great. Yep. And I'm starting to see hints of that with WASM, like modified kubelets that run WASM binaries that are not containers. Do you think there's a future for Kubernetes where it moves away from being container focused and it's just like, yeah, most of these workloads are containers, there's a bunch that aren't?
I believe the only scheduler on this list that required a container was Docker Swarm. Like Kubernetes and Docker Swarm. Everything else, like Borg was a C group, right? It wasn't actually a container, it was nothing. Mesos would exec out. There was even a runtime for Kubernetes early on that would do a systemd, right? And I feel like Twine is CoreOS Fleet on steroids, right? Like someone like ran with that because all of Twine is systemd under the hood. It's just systemd execing stuff. And I do think that that flexibility is nice to have, but that flexibility comes with the complications of now I need to figure out like that, where does that runtime go? The Mesos model is every framework had its own kubelet basically. You ran a framework and then you ran that framework's kubelet on all the nodes too. And so the more frameworks you had, the more kubelets you had, but also that meant you could run two of the same framework, different versions in the same cluster, and it didn't matter. And you could say like, oh, I can upgrade one framework at a time, or two different teams get this thing, and makes that side of it flexibility to say, oh, the Mesos piece stays stable forever.
We actually had a framework for DCLS that ran Kubernetes clusters in Mesos.
Right. I remember that. Like when they started shipping Kubernetes on top of Mesos, I'm like, yeah, it's just a framework. That makes sense. It's a platform side of it. And Kubernetes is the platform for platforms, but don't give you the framework piece. And all of the frameworks that were opinionated, like Aurora from Twitter and all of these things, were like, no, we run this type of workload really well. And if you want to exec out, you figure out how to get the binary there, right? The distribution model of containers was mainly because people were really bad at like mounting NFS and putting binaries on systems, or they would put all the binaries on the system. You're like, wow, I got a 100 gig image that I have to somehow install everywhere. And that sucked too.
Yeah. Great talk. What about schedulers? You mentioned that Kubernetes, one of the examples had like a scheduler that look at what things have been running for a while. But in Kubernetes, we have the the default scheduler that I think everybody uses. But we also have the extension to have multiple schedulers, and there's a repo with different type of schedulers. And we also have things like sick bash of like doing scheduling for job or batch. So do you think we have a problem with like too many schedulers, or it's just a matter of like, people are using the default one, and then that's what people go with?
My intro, like I was dead set at Disney to use Mesos. I was like, this works for us for our render jobs and all that stuff. And then I have an origin story that a lot of people have in Kubernetes where I had lunch with Kelsey. And I was like, the thing I don't like about Kubernetes is you can't have a custom scheduler. He's like, you can. He's like, it's in the API, we just don't document it. And so I spent the next 2 weeks writing a scheduler in Bash. You can go find it on my GitHub. I was just like, oh, would I do this in Bash? And like it lowered the barrier for like you can build something flexible. And I think the problem with a lot of the things we have now in Kubernetes is they don't have enough opinions. They're generic to say like, here, if you want to run batch jobs, go over here, and here's a billion things you can do with it. And it's not what we had with Mesos with something like Aurora. And it's not like, and Borg has the same problem. Borg's Borg config files, like I hear about like how horrible those were. They compile to like a protobuf. Like you compile like this big like thing into a protobuf file and like a little metadata about the I'm like, what are you doing? That sounds so obscure. But they're like, we can do anything, and that's why this platform's successful, because we can do everything. And I'm like, I don't think people want everything. A lot of people want, give me some opinions and make me fit my application into it. The best decision we made at ECS for our platform that we built is we said no. We told people like, actually, you have stateful workloads, don't come here. You can shift your workload to run on ECS in the way we run it, or you can go somewhere else and have fun, right? And we got like 70 to 80% of Disney Plus ran on our ECS clusters because we said no, and they refactored. I'm like, actually, I do want that thing. I don't want to deal with all this other stuff. And so by having some opinions about it, and I still say that every platform engineering team, the best thing you could do is tell someone no and say, I'm not solving your problem with this platform. And being able to have that opinion is really, really good. And the problem with all of the schedulers, the Kubernetes scheduler is advanced. Like once you go into like, I want to tune the Kubernetes scheduler, you're like, actually, I can tune too much here. I wish someone would just like give me a little bit less information about how I might want to schedule this sometimes. And I wish we had more independent schedulers, like Volcano is one of them, right? Like, and those are the ones that are like, oh, this is really cool because it's only meant for this type of job and not for the other things. And if I want to schedule my workload to it, I can change my metadata. But I wish we had more smaller, opinionated, not generic things. And I feel like all the Kubernetes stuff generically blows up to, here's 50 CRDs, have fun.